getting clear?
Yes.
Okay, so we will continue the problems from the assignment from the week 6. Okay. So these problems today, whatever we are discussing, it's a problem similar kind whatever there in the assignment in week 6. So the first question is, the following engineering stresses produce the corresponding plastic engineering strain for a brass alloy prior to necking. Determine the engineering stress necessary to produce an engineering strain of 0.25. So the values are given, engineering stress and engineering strain, and you have to find the engineering stress for the engineering strain value 0.25. So which formula you have to use for this?
Yeah. This true stressful.
Yeah, true
Hmm.
stress and true strain formulas.
Hmm.
Okay, so what are that? What is true
Sigma is
stress?
equal to S into 1% and epsilon is equal to S
Sigma into
1%.
1 plus epsilon, and true strain will be
S 1%.
epsilon is equal to log 1 plus CE.
Hmm.
Right. Mm.
Hmm.
Now, what you have to find? First of all, you have to find the true stress and true strain also. So, if I make a two column here, it will be true stress and here strain.
Sorry.
So, find the value for these two. If the engineering strain is stress is 235, then what it will be for true stress, and engineering strain is 0.194, what will be the true strain? First of all, you calculate these two. And please let me know what is the answer you are getting.
Yeah, done.
How much you got true stress here?
280.59.
Okay, 280.
280.
Yeah, that is correct. And what about 250?
314.75.
314 or 324?
1, 2, 6, 2. Yeah, sorry, 3, 2, 4.
Yes.
Uh,
It will be 3 to 4. And
hmm.
what about 2 strain value you got?
0.177,
0.177, then
0.59.
0 0.59 or 259. Just cross check once.
And then point 2. Now 0.259.
Yeah,
Alien,
0.259.
uh, alien 1.296 equal to 0.259.
Okay, now let's see. We have to find all these values for which one? Engineering strain which is given 0.25. So for this 0.25, first you have to calculate the true values once, then you have to find the engineering stress value. Okay, so if
Sorry.
you no, you have to find the engineering stress value for 0.25, right?
Hmm.
But there is no connected formula for engineering strain to
Yes,
engineering
yes,
stress. So what
yes,
you have
yes.
to find, you have to find the true values of this 0.25, then you have to find the engineering stress and strain.
Acha, acha, acha. Okay.
Okay, so now what will be the formula? Do you remember the formula what start taught in class? Sigma t is equal to k epsilon
To the
w
end.
prime. Right, no? So
Uh,
so you can take log on both sides. So log sigma t is equal to log k plus
and epsilon.
n. Yeah, it is n log
And,
epsilon t. Okay, you can take it as epsilon t because it's true value.
uh,
Now you have to get the two equations. Like here k is constant. You have to find the k value and you have to find the n value. So
hmm.
the two things we know already. We will make two equations from the known. So you can write log.
Can we take this uh, n is equal to k?
No, no, you cannot take it. You have to find it.
Okay.
So it will be n log 177. This is first equation. Okay, and
Hmm.
second equation will be log 324 is equal to log k plus n times log 259. Now you got two equations. Solve
Hmm.
these two equations. Like subtract it and you will get the value of n. And find the value of n. Similarly, substitute that n value any one of the equation and find the value of k. Okay, please try it. Solve these two equation and find the answer for it.
Quite lengthy problem.
Not lengthy but calculator needed. That's it.
Sure, what is the value of n?
In we are getting 0.38.
Yes, 0.38. Okay, fine.
Got it right? Same.
Hmm. Just let me ask.
Friends, substitute these in any one of the equation and find the
Uh-huh.
value of k.
What is the value of k?
How much you got? It will be 543.
543.
Yeah.
Just tell me one thing. What is the value of this log k is coming?
Mm,
It is 1.593.
yes, we'll tell you that. How much you got? 1.58.
Log k is equal to
Huh,
1.593.
yes. And
Then
if you find the inverse,
okay, what I have done, I have done this k will be equal to 10 to the power 1.593.
oh, you.
Then it is coming 39.174.
You try once, okay? It will be 543.
Okay, fine.
You check it once later, okay?
Hmm.
Now this is not the solution. Now you have to find. So here we got the n value will be 0.383 and k value will be 543 megapascal. Okay. Now from this, what you have to do? You have to find the sigma t value. Substitute k and epsilon t value to the power n. Then you will get the sigma t.
Okay.
Okay, like 543 megapascal times 0.223 times means to the power how much? 0.383, and you will get the sigma t value, that is true stress. And if you know the true stress, then you can find the engineering stress from the equation, right? Similarly, you can find the
Quite lengthy problem.
it's like a numerical kind of, but it's asked in earlier assignment, okay? Last year.
Sigma t it is 305.
Sigma 306, 3 for 5.56, right?
It is a 5.306.
Then what about sigma value?
244.8.
244
8.
yeah, that is 245. See the option B.
245.
Option B is the answer.
245.
Yeah. Now we'll go to the next problem. The problem is it like theory kind of. So the question is, which of the following is true regarding the true stress strain curve and engineering curve? Okay, which one should be true? That's the question. So first question, the true stress strain curve shift up and to the left of the engineering stress strain curve before necking. The option B is the true stress strain curve shift up and to the right of the engineering stress strain curve before necking. The true stress strain curve shift down and left to the
Upward, na?
engineering stress. Then
Yes.
both are identical. So which one will be the answer?
Hmm.
So this is the stress strain curve, right? One is
Hmm.
engineering, another one is true. So what is
Hmm.
happening here?
True one is above on to the engineering.
Shift. This true will be shift up
Hmm.
for the engineering and to the up and the left. Right.
Hmm.
So that's happening here. See here.
Hmm.
So that's why we can say the first option A is correct.
Hmm. Hmm.
Okay.
So, sir, today only I am there. I mean, you have to invest your entire time only for me. I mean,
Any other students will listen the video later, right?
okay, fine, fine, fine.
Yeah.
Otherwise, we can live.
No, anyone to take.
Hmm.
Yeah. So the next question is, determine the tensile stress that is applied along with the 1
Again,
minus.
this is a long calculation. We have to
Uh,
calculate what happens then this
yes,
here
yes,
is
yes.
this
You have to
sigma
calculate.
by A cos lambda cos phi.
P cos lambda by A over cos phi. Yes,
Uh-huh.
same thing you have to calculate. So, and cos phi you have to calculate. It's little bit
Uh-huh.
lengthy, but it came in the exam and assignment.
अच्छा
So
अच्छा
you have to do. So the question like applied along with the 1 minus 1 0 axis of a silver crystal to cause slip on the 1 minus 1 minus 1 and 0 minus 1 1 system. Okay, so the CRSS is 6 megapascal and the
हम्म
addition of alloy element is there are two questions. Okay, one is you have to calculate the tensile stress and another one is you have to answer the second question, addition of alloy
increases
element increases or decreases
increases
whatever it is.
increases
It will increases. That is true. So
increase
the second answer is increases. But what about
increases
the first answer? It is 10 power
after
8 because
calculate
yeah.
yeah
So
just give me a minute.
this is the figure, right? So you can
Hmm.
see there is axis and this is 1 minus 1 0 which is given and 1 minus 1 1 that is the slip plane normal and slip plane direction also which is given. Now you have to calculate the phi value, cos phi value as well as cos lambda value. So what will be cos phi and what will be cos lambda? So how to find it? If
Okay,
you know
just
H1,
checking with you.
yeah, K1 L1 and H2 K2 L2. Okay, then how it will be? There is one formula for cos angle, right? Cos phi is equal to H1 H2 plus K1 K2 plus L1 L2 divided by root of H1 square plus H2 L1 square plus K1 square, okay, times root of H2 square plus L2 square plus K2 square. So you have to do all this and find the cos phi angle. Similarly, cos lambda also. So cos phi angle between these two planes because here is the phi angle. Similarly, cos lambda will be these two. Solve it and please let me know what is cos phi and cos lambda first.
14.7.
Yeah, 14.7. So here you will get the cos value will be 6 over root 2 over root
2.
6 and
Yes, 2
cos
by 6 and a
alpha
half.
1 over 2. Okay, then what you have to do? You have to apply.
6 into
So
6.
C to R SS will be P by A cos phi cos alpha. So this is a general formula, right? Otherwise, what you can do? You can solve. So it will be P by A means your sigma value. So it will be 6 is equal to sigma star times 1 over root 6. If you do cos alpha cos phi, the both will cancel, 2 will cancel, 1 over root 6 will be there. From there you have to find the
14.7.
yes, it will be 14.7. Okay,
Okay.
now next question. Which of the option is true?
None of them.
So okay, first option slips
Option
occur
B.
when two neighboring grain slides against each other along the grain boundaries. That is wrong. Anyhow, slip system are described by what else? If it is not a combination of slip planes or a strain field, what is depending on?
Sleeps. Sleep and sleep direction.
Yes. So here it should be
None of the above.
slip's directions. Okay. And when a material is stressed above a critical resolving shear stress, making starts. That is also wrong. So the answer is none of the above. Then, what about the fifth question? What do you mean by work hardening actually?
Increment of strength with deformation.
Okay. So which option will be here? Absence of any slim system.
Increase in dislocation density. And also, nice, increase in dislocation density. Option B.
Option B. That is correct answer. What about for sixth question? Which of the following is or are correct? There will be more answers, not only one.
D and D.
B and D. Why B?
Because equal to in generate due to plastic deformation.
Then what about option A? What will happen in the single crystal? Like B and D are same option, right? So this is true, definitely. But one more answer is there. Option A or option D. The stress strain curve of a single crystal undergoing twinning shows jagged irregularities, or deformation by twinning is a dominant mode of the deformation in FCC method.
C is not true. A, I am not sure.
C is not correct. FCC method it's not like that.
A, I am not sure. I mean, I have never seen this type of
A is
graph.
correct. For single crystal, twinning, twinning shows the jagged irregularities.
Okay.
So
And this type of stress strain curve is given in the slide. I mean, I don't think so.
maybe sir mentioned in the class just by words. So what will happen for a single crystal? If you like when the tuning starts, what will happen? The dislocation density will also change. No. Wait.
No. Twinning is basically one type of obstacle which is analogous to grain boundary.
Irregularities will come, like in case of a single crystal. That is
Okay. Can you provide me any stress strain curve which shows this kind of thing?
I had to check it. I
Yes.
didn't check for it. I'll check it. If I get, I will include in the PPT.
Okay. Thank you.
Yeah. Now seventh question.
Sorry.
Which of the following is true about deformation in single crystals and polycrystals? Okay, I can show here stress strain. Yes. The answer is B here actually, but just go through the stress strain curve. Okay, one single crystal and polycrystal. So, what do you call this region? The red color one.
Which question?
This is till here.
True elastic thing.
This is elastic region, right? So Hooke's law will be obeyed here.
Hmm.
Then this point is what we can call this transition point. Yield. Right.
Yield point, yes.
Yield point. Yes. Now, same thing also, but same also happening in the single crystal, but it's like a very smooth way. So here is the initial stage. From here to here, here is the initial stage which is happening. Okay, and here the strain hardening is happening. Okay, then yielding, like this higher part. Okay. Now see the single crystal do exhibit the initial stage of easy glide. So yes, initial stage is present. Okay. Single crystal tends to have a lower yield stress than the polycrystalline. That is also correct. And yield strength of a polycrystalline with the grain size of 100 micrometer is less than the yield strength of the same polycrystalline with 100. So that. So see here, like increase the when this is the plot like where we are increasing the grain size. What is happening to the mechanical property? Like it will be strengthened, or it will be toughened, or it will be ductile, whatever. Okay. So from that you can understand from this curve.
We can directly also get from this work based relationship also.
Yes, we can get it, but this is also one solution. So here answer is all of the above. Okay.
So if you find that please include that, I mean that twinning jack or
irregularities part, right? Okay, I'll check it. Now, what about this? Substitutional solute atom in results in dash and industrial atom is dash. So which one will be symmetrical? Which one will be non-symmetrical? Substitutional or industrial? What is
No,
the
no
answer?
symmetrical, symmetrical.
Hmm. Non-symmetrical and symmetrical. Really, like substitutional solute atom means like, okay, I can see here industrial big substitution, small substitution. So where the symmetrical stress field is coming, where the non-symmetrical stress field is coming. If atom is substituted, there will be the symmetrical.
Symmetrical,
Hmm.
symmetrical.
And if it is a interstitial, what will happen? It will be non-symmetrical.
No
So which
symmetrical.
option is correct here?
Uh, Option A.
No, option C, right? When
Uh,
interstitial, it is non-symmetrical.
uh, no symmetrical.
Option A,
Option
both are
C.
symmetrical.
Hmm.
Yeah. Now, the ninth question. Which of the following is are true about the yield point phenomena? Definitely more than one answer will be.
ABC.
ABC. Then what about
Sorry, BCD.
BC? This is the
BCD.
correct
Uh,
answer. So for a yield point, what will happen? The upper yield point corresponds to when the dislocations are located in due to the presence of solute atom in the low carbon steel, right? And the lower yield point corresponds to the occurrence of slip when the stress drop down drastically because locked in dislocations are set free. And the D is in high carbon steel no yield points phenomena is observed. So answers are B, C.
BCD.
Yes. Now next question. Which of the following process can be used to refine the grain structure?
Recrystallization.
Okay, these all are like which process?
Recrystallization.
Recrystallization, no, which method? Like recrystallization, recovery, grain growth, all this will happening in annealing, right? Okay, I can show the figure here. Like answer is recrystallization, no doubt in that.
The process is such
Okay, so see here,
recrystallization.
it is when how the grains are changing. So in this recrystallization part only, the
This
grains are
transition
changing.
occur.
Yes, refining the grain structure.
Hmm.
Okay, now next is a small problem. Consider a pure silver metal specimen that has a dislocation density of 10 to the power 4 millimeters, like per millimeter square. Now imagine if all the dislocation present in 1000 millimeters cube volume were somehow displaced and linked end to end. How far would be the chain extended? So dislocation density is equal to dislocation length by volume. That is the formula. Both are given, you find the answer for it.
How can you solve it?
What?
How can you solve it?
Use this formula dislocation density. Dislocation length they are calculating.
Oh, okay, 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 fine, fine, fine.
It's direct question, just you have to
Uh-huh.
find.
10 kilometer.
Yeah, 10 kilometers.
Hmm.
One more answer here. It will be 10 to the power 7 millimeter that you can consider. Now, this problem.
Similar method is that would
Hmm.
can do it.
Yes. Just
Okay.
like you say, what will be cos phi here?
Acha, acha, okay.
If you say cos phi here, you can directly say the answer here. Schmidt's factor. What is Schmidt's factor here?
So we have calculated. Just give me one second.
Hmm.
Is it zero?
Yeah, it's 0. Cos phi will be
Uh,
0, right?
ah,
Yeah. Then what about the solid solution? Have a higher yield strength than corresponding pure metal because they have larger grains. They contain more dislocation. Dislocations are more difficult to move. Dislocation causes the work hardening.
C.
Yeah.
Option C.
Yeah, the first question, right?
Hmm.
Yeah, first question option is C. The question is the
Hmm.
under coestostatic loading the stress at different location with gauge length is different. The answer is same at all with the all the point
Hmm.
before necking. Yeah, that is correct. And what about the second question? The question is if
Hmm.
sigma
A. A.
yeah, if sigma denotes the true stress in the material and S denote the engineering stress in the material, then the relation between sigma and S. How to find it?
From this volume constancy.
Yeah, like sigma, it will be load
Hmm.
divided by instantaneous area, right? So this you can
Hmm.
represent as P by A. Okay,
Hmm.
and engineering stress, yes, how you can represent P by A0.
Hmm.
Where what is A0? A0 is the
Original cross sectional
original
area.
cross sectional area. Okay, now true stress will be what? Sigma is equal to P by A0 divided by A0 by A.
Hmm.
Okay.
Hmm.
Now, as per the volume of the sample does no change during the test, right?
Hmm.
So then we
Hmm.
can write
Hmm.
V initial will be V final.
Hmm.
So A star L is equal to A0 star L0. From this you can write it as A by A0 is equal to L0 L by
Hmm.
L0. Okay, it will be L0 by L. Okay. Now we the A by A0 is like A0 by A
Only
is
we have
what?
to replace it.
E plus 1,
Hmm.
right? Then we can
Hmm.
write it as sigma is equal to P by A0 times E plus 1. That will
Hmm.
be S times E plus 1. Okay,
Hmm.
this is the relation.
Hmm.
Now, next question. The formula of true stress in a material after necking is given as
B. Oh, after nicking.
hmm,
B again B.
D. No, it is
B. B. B before boy.
no, it is C.
A
A
neck.
neck, right?
After nicking.
Hmm.
But this true stress represents instantaneous cross-sectional area. Na?
That is before necking, right?
If we go by the definition, I mean, uh, okay, maybe right.
You go through once again SARS class, okay? This portion. Just
Mm.
we'll check it. Now, what about the question A? If sigma 1 and sigma
B.
2, sigma 3 are the principal stresses acting in a material, and sigma
B.
1 greater than sigma 2 greater than sigma 3, then the maximum shear stress acting in the material as per Tresca's criterion is given
B.
as option
B.
B. Yeah, sigma 1
Mm.
minus sigma 3 divided by.
Mm.
Now, next question.
The maximum temperature. Shear stress acting.
The maximum theoretical shear stress acting in a material with cubic crystal structure is approximately given as.
A.
No, it will be C. Option C. How you told it is option A?
Forget the how can I calculate it? I mean, How this E by 70 is coming? You have to remember this value or tell.
One minute.
The star max.
Yeah, so max only I have to. You have to calculate same way. X0 cos alpha divided by A0 divided by A sin alpha.
Wait,
Right. Yeah. Use that and same. This you already know. Use the formula, but cubic system you have to find the alpha value and what it will be. It will be 45.
sorry, how?
Same. Tomax equation you know, right? Maximum stress, shear stress. It's already explained in the class, I think.
Tau max will be equal to
Sigma 0 cos alpha sin alpha.
uh, what should be the value of alpha?
Alpha is the maximum value, it is 45. But for cubic system,
So then how can I correlate this E?
you can correlate with Young's modulus, right?
Uh,
Okay, we'll check it.
is it possible kindly upload its this solution?
For cubic crystal, right?
Yeah, thank you.
Then what about question C? 6.
Reason is wrong.
Reason is wrong. What is the correct
Okay.
answer?
Hmm?
What is the correct reason for it?
See, these pairs are not closely packed.
This is. Okay, fine. Now next is like slip will always occur
45 degree.
it's always at 45 degrees.
No, no, actually, no. B. B.
Yeah, there will be, it is.
Sleep system, even though it is not
Yeah.
making 45 degree with the principal axis.
Yeah. Now next you have to solve it.
It is the same problem, no? 40.7, 6 MPa, 40.7. Option A 40.7.
Yeah,
Hmm.
same.
Right.
So here how to solve this? Here actually cos phi you have to find first, right? So it will be
Yeah, you have already solved it.
yes, but I'll write it now. In some other students, if they listen this, there is 0 minus 1 divided by root 2 times root 3. It is the same formula, but we have to use h1 h2 plus L1 L2 plus K1
K1,
K2
K2.
divided by root of h1 square plus h2 square plus L1 square plus K1 square and root of h2 square plus L2 square plus K2 square. Then you will get cos phi like this. So the answer will be 2 by root 6. Then similarly, if you find cos lambda also, you will get 1 over 2. Then sigma will be p by a stars cos phi stars cos lambda. Substitute all the values, 6 times root 6, it will be 14.7. For a given tensile stress, the resolved shear stress in a material is maximum minimum when the Smith factor value is what? Smith factor value will change from
1 and 0. Sorry, half and 0.
half and 0 or 1 or 0. If the CRSS value is maximum, what is the Smith factor?
45 degree means half, na? Oh, sorry, 1 by root 2. Half into half.
No, CRSS is there.
Yes, maximum for 45 degree. Half sigma.
It will be 1, right?
No. CRS is maximum when lambda is equal to phi is equal to 45 degree. So that the result shear stress will be equal to half sigma. Half and 0.
Okay. Now what about the next question is winning crystal reoriented itself such that We'll
Highest
yes,
highest
high
click
Smith
factor.
strain, a high Smith factor or factor 0 of strain. No relation between Smith factor. Which one it is?
High Smith factor.
Yes, high Smith factor. The next question, the figure shown below is idealizing
B.
stress, the rigid ideal plastic material or ideal plastic material with
B.
elastic region,
B.
linear strain hardening material, ideal elastic material. It will be
Option B.
ideal plastic material with elastic region.
B.
Yeah. Next one, strain hardening will be highest in HCP material at a high temperature, HCP material at a low temperature, in cubic material at low temperature or in cubic material at a high temperature.
B.
Mm-hmm. How you are saying it is B?
Because number of sleep system will be strain hardening will be highest. Sorry, cubic material in low temperature.
Hmm. Yeah, that is
Cubic,
the
yeah.
answer. Now, 13th question you have to find it. A tensile specimen with a 10 millimeter initial diameter and 20 millimeter gauge length reached a maximum load at 9,000 kilogram and fractures at 7,000 kilogram. The maximum diameter at fracture is 8 millimeter. The engineering strain is strain at fracture is. So you have to find the engineering strain.
Strain at fracture. How does I solve it?
Yes. So what will be the formula for true strain at fracture? Epsilon is equal to 2 log d0 divided by d, right?
Mm.
And the epsilon
How can I
value,
give this equation?
this is the formula actually.
Okay.
Then epsilon f, we already know that log, same log e plus 1, right?
Epsilon is equal to
And
0.4.
this one will be the engineering strain at fracture.
One sec.
So now you have to find the engineering strain at fracture. So do the exponential on both sides, then log will cancel here, then minus 1, then you will get the epsilon value.
Zero point 0.56, that means option A. Option A.
Yeah.
So we have to remember this relation epsilon A is equal to
Yes,
2
yes, you
ln.
have to remember.
Oh, okay.
So not it, okay?
Mhm.
So the 14th question is, if the true stress true strain curve after yield point is given by sigma is equal to 130 e to the power 0.33 megapascal, then flow stress of the material at strain 0.5 will be of the material. The options are 103 megapascal or 153 megapascal 5 or 93 megapascal 5 or 123 megapascal. So please try to solve it first with the same formula. Sigma is equal to 130 epsilon 0.33. Then you will find the answer for it.
One zero three.
Oh, yes. Okay, now the next question. A steel wire is attached to mass of 5000 kilogram. If we have to design a wire, then what will be the minimum diameter which can lift the load without any permanent deformation? So UTM of the wire material is 600 megapascal and yield strength is 2 by 3rd of the UTM. So here you have to find the diameter, minimum diameter which can be lift the load without any permanent deformation. Did you get the answer?
Yes.
How much?
Indeed.
Yeah, how you did it?
Mm. See, the sigma y is equal to 400 MPa. I mean, that is which the y is.
Hmm. So which formula you used for sigma?
5000 by square by 4 into 9.8.
Hmm. Oh, okay. Into 9.8. Yes.
Mm. Actually, it's coming precisely 12.4, not 100. It will come to the 0.6.
Oh,
I
okay.
mean, the range. 12.4, maybe 12.5.
So these are the kind of questions, okay, from the last session, 6th week class. So you should know the formula about engineering stress, true stress, engineering strain and true strain. So you should remember these formulas, okay, and this one also. Similarly, stress strain curve for stress strain curve you have to remember like engineering curve and true curve, because four problems will come from that. And this formula, cos phi formula, it is little bit lengthy but you need to remember it. And this one also, tau RSS value, okay. And then some basic questions you should know, and you should know the single crystal things. So here you can see that a single crystalline and polycrystalline stress strain curve, so you just go through it. And then substituting the and interstitial and small substitution, interstitial defect, you should know how it will be symmetric and which one will be non-symmetric cases, okay. And you should know about the annealing and recrystallization process and etc., how the grain boundary look like. And the dislocation density you have to calculate, like you have to know how to find it. Then you should know like same cos phi, cos alpha problems, like things, and solid like dislocation things. And one more important formula here, sigma values and S value. And what about this plastic material, elastic region, hardening, toughness, ductility, these all things also you should remember from the week 6 class. And this formula, this is also one of the important formula you should remember for the fracture case. So fracture part also important, okay. That is normal formula. And the same method, like you have to remember how will be the force acting on the system, how can we can find the diameter values. Okay, I hope you understood all this, right? Okay, so please go through the lectures, whatever are taught in week 6. So next week class we will solve week 7 problems related to week 7. Okay. Okay, then we will meet in the next class.
Thank you.